All right. Hello, everyone. Thank you very much for being here. Good afternoon to you. Let's start by breaking the ice a bit. Who knows Akka streams here? Few hands. Right. Who has used it in anger in prod? Not not that much hands. So that's kind of expected, and it actually proved my point. You might ask, what's the point? And yeah, that's I'm gonna go on and explain it in a second. So there's a constant buzz about Akka streams and reactive streams in general. Whenever you need to handle infinite streams of unbounded data of like uncertain volumes, then that's where you want reactive streams. They employ asynchrony and back pressure, and they allow you to build these awesome, elastic, and resilient pipelines. Yeah. So it's also very easy to get started with them. With the example of Akka streams, for instance, there's plenty of things you can play with online, as you probably know. It's just a simple library. Yes, you just download it, you start playing with it. Super simple. Although at some point you're likely to want to move to something production ready, right? Something production grade. And that's the step we're going to talk about today. This step is not always easy, and it's what we'll focus on, right? It's a feeling that you might have experienced before. It happens to me all the time. You start with something simple, right? You build something simple and it works, right? And you're super happy and empowered by it. Although when it's time to move to something slightly more complex, it can bring some level of agony and despair, right? So very simple examples are very helpful at helping you grasping the concepts, but they don't get you very far when you're building production systems, right? So this talk will try and offer you a perspective on that, and it's going to hopefully give you a few patterns to use to design and implement production grade pipelines with Akka streams. So first thing first, as mentioned, this is me. I'm an engineer at HomeAway in London, UK. HomeAway, if you haven't heard of it, is a brand of Expedia Group, and it's essentially a vacation rental marketplace. At HomeAway, we build a lot of data pipelines for a variety of reasons, and this is why I wanted to give you a flavor of how we think and build such pipelines. And I'm going to do it by example. So the example problem we'll tackle today is in the sphere of digital marketing. So the example that you see here is one of our dynamic ads, right? So for our advertisement to be as effective as possible, we want it to be to some degree dynamic, right? We want to show relevant content to the relevant people. So let's assume that someone was on HomeAway and they was taking a look at this nice cheap villa in South Africa, but in the end ended up distracted by something else, maybe a video of cats somewhere. And this is a very good opportunity for us to display something like this to him to try and lure him back to the site to convert, right? This is probably something you've seen before. So we use stuff like Google AdWords, Facebook, and others to display these ads. Now, the key point is that these platforms that we use, they need to be up to date with the data that we have in our systems, right? This data can change a lot, especially the price. We've got a lot of things to send there. We've got images, we've got the details of the property. So for this strategy to be effective, we want our data to get to these platforms, and we want it to get there as fast as we can. So our objective is to make this a programmatic feed, right? So we want to set up automated feeds from our core platform to these ad platforms. And our key requirements is that we want these feeds to be resilient and elastic, right? So there might be some throttling, some batching, depending on whatever we have on the other side of this pipeline, right? So situation like these, like gluing heterogeneous system is exactly where Akka streams shine. So for the purpose of this talk, we're gonna try and build an example pipeline, and we're gonna assume we have a flow of property data changes coming from HomeAway, and we want to validate this data, and we want to send it over to Google AdWords. So this is going to be necessary to keep them in sync with our stuff, right? As said before. So for this example, suppose we have a KAFKA feed on the left-hand side, and on the AdWords side, we have an HTTP API. This is actually a simplified view of the feed that we have in production right now. So this is our problem. We're going to try and tackle it in 4 different phases. So we're going to touch on these 4 different aspects. We're going to first try and shape the stages of our pipeline. we're going to try and give them types, and these are gonna drive the code and the tests for our systems. So first step, break down into stages. So first of all, what are stages? It's a great question. I'm glad you asked it. This is borrowed from Akka Stream's lingo. So stages, you've seen it before, I'm sure. It's a reactive component of arbitrary complexity. It comes in form of source, flow, sink, whatever. These are the sort of Akka Stream's kind of keywords in a way. So they're distinguished by their shape. So they're distinguished by their output and input ports, right? So source has got an output port and so on and so forth. So stages, as said, they are composable, right? So they have great composability. This means that you can take a stage output port, connect it to a stage input port, and make a new stage with a new shape, right? This is pretty trivial. So you have a source and a flow, compose them, you still have a shape with one output, so you still have a source, right? One special case there is the runnable graph you see at the end. So this is a stage that's got no ports at all available. So you've connected basically all the ports that are there. So if you have a source and a sink, you connect them, there's nothing left to connect, you've got a runnable graph. And this means that you can run it. So you can call a run method on it. You can basically feed this graph to the Akka Streams infrastructure. Something called materializer there, which we're not going to see in details, but essentially you actually start the flow of data through your pipeline. Now, composability rules here are really simple, but they tell you something very important, that you can, and you actually should start very simple when designing your pipeline. You have to design your pipeline starting with a few simple stages and then use composability to incrementally deep dive into them to handle the complexity. And getting your abstraction layers right is key when your pipeline grows in complexity. So with this in mind, let's try and go back to our example. So these are the integrations that we set up before. What are we going to do next to identify our stages? So the first step is kind of trivial. We want to set up a source for any integration that consumes data and a sink for any integration that produces data, right? So now what happens in the middle? Like at this point, requirements could be kind of fuzzy, as they are most of the times. So it could be something massively complex, something very trivial, or anything in between, right? So again, it's important to start very simple. So firstly, we can envision a flow that masks all the complexity that might need later on. So all of this will be wrapped with a runnable graph, of course, as mentioned before. You need one of these if you want to run your stream at any point, right? So you're likely to want something like this. So these are the stages composing the pipeline. So the next step we're going to try and take towards building it is identifying the types, right? So we find it's very good practice to think about the types of the pipeline and let them drive your code next. So this is something akin to maybe type-driven development, maybe even event storming that was mentioned in the keynote. So every Akka stage has got a type signature, and here you can see type signature of a flow. Now, this is like Scala syntax, but of course Java doesn't change. So the flow, going from left to right, you're going to see first the types of the ports. Now, in and out, flow is like one input, one output, so you're going to have two types there, easy. The third type, the last type of the signature, is the type that every stage is guaranteed to have, and it's what's called materialized value. You might have heard of that. A materialized value is something that Akka Streams gives you back when you run the stage, of course, as part of a broader graph. Now, from a practical standpoint, is essentially your chance to interact with the stage while it's running. So after you run your flow, maybe you want to interact with that from the outside code, and maybe you want to stop the flow of, if you want to, for example, kill the stream at this point, that you can expose something like a stoppable object here, or any trait that might expose any functionality you might need. Now, there's also the possibility that you don't need any interaction at this point, and for this purpose, Akka provides an object which is called NotUsed, which you can use in your type signature to signal the fact that the materialized value here can be safely discarded. Now, if you move back to our example, we can start and think about the types here, right? So our source will be a source of some events. We can call them property change here. And our materialized value is not used here. Now, why is the case? We want this pipeline as set to be always on, right? So we don't want to stop consuming our events from Kafka. So we signal here to whoever reads this type signature that we don't need any interaction with the source itself. Now, in case again you want to be able to shut down the Kafka consumer in any way, you might want to expose here some kind of trait like a shutdownable trait or a stoppable trait, right? In this case, we're just keeping it simple. We just want to set it always on. Now, the flow itself is going to consume these property change events, and it's going to produce another kind of event, which we can call adverse change, right? This is the transform data we sent forward. The sink will be ingesting these changes, and if you can see here, it's the first time we use actually a materialized value. Now, this is it's a future that will complete when the stream is complete, right? So you might argue, okay, but your pipeline is always on, so why would you ever need to care about this? Now, it's true. In the vanilla scenario, you're never gonna see this guy complete, but because something could go wrong, it's always a good idea to kind of expose it somewhat. So you might, react to the completion of this future and maybe log or do something else. Now, this is the graph that wraps everything up. Again, only one type for the graph, that's materialized value because it doesn't have ports, right? So the materialized value here will reflect anything interesting that's materialized inside your stages. So if you can see, the source and the flow, they don't use anything interesting as materialized value. We just bubble up the future that comes from the sink at the graph level. Now, it seems we have an end-to-end pipeline, right? We've typed the stages. Now, the million dollar question is, do you like this? Is it something you might go to production with? Now, suppose you ingest a property change that is not valid for any reason. So we want to do validation logic here, right? So what's going to happen? It's not clear, right? So we don't know from the type signature standpoint what's going to happen in case of a validation error, right? Now, actually, looking at this signature, one might even assume that no error is possible here, right? So the key exercise is to try and hunt down all these side effects that might happen. So consider anything that you can handle as side effect in a productionized application. So you got error handling, monitoring, logging, auditing of any kind. The key step is to try to convert these into regular events flowing through your pipeline. And this is something to some degree recommended even by the Reactive Manifesto. So event errors should be treated as regular events flowing through your pipeline. This allows your processing to just proceed without any special action or interruption, right? The errors are just propagated downstream as any other message, right? So this is not just valid for errors. You can do the same with audit messages, any kind of metadata that you might want to record through your system. So when designing your stages, this basically translates into much richer, complex types. And these on the slides are just a couple of examples, right? So for example, the first one is something that can produce, a flow that can produce either an error or a result. Now you can have, the second one is something that always produces a result, but also produces a bunch of audit messages, for instance, which might explain how the result was calculated. Third one is something that is kind of a pass-through flow that carries over some kind of offset that might be coming from Kafka. These are just examples. There is no silver bullet here to nail, of course, the type. But each stage semantic must be analyzed properly in order to nail the right type that might convey what's going on inside the stage. So from now on, we're going to focus on the error handling case only. But again, keep in mind that any kind of same rationale could be applied to auditing and any other side effects. So going back to our example, our flow can be changed to produce either a validation error or an adverse change, right? So this is much more transparent. So this enables separation of concerns downstream. You can actually have a sink that handles the errors and a sink that handles correct changes, which goes out to Google AdWords, right? But clearly errors are just not bound to happen just in this specific case, right? We could have errors in other places, like we could have errors actually coming from the sink that talks to Google AdWords, right? For example, the server you're trying to contact is not there or whatever. I mean, anything can go wrong. So we need a way to generify this behavior. And a way to do this is to introduce, for example, another flow for the AdWords logic that can produce, again, either a storage error of some kind, or in this case, some positive signal. We can call it stored here, right? So what we can do now is have one sink that is able to generically handle both errors that can happen in your pipeline if you set them up in a hierarchy correctly. Now this has the advantage of, again, handling all the errors in the same place. So we're just going to stop here with the exercise of making these types as expressive as possible. Now, just for the sake of this example, we're gonna just assume we like this first cap topology here. There could be more refinements that we could do here. For instance, there might be errors even in the source when deserializing stuff from Kafka, right? So there might be more to be done here from the type point of view. But let's just assume for the sake of this example that we're fine. So we can now move on to the implementation, right? So we can take a look at these stages one by one and see how we can implement them at this point. So we've nailed down the type, so we're going to start with that. So here's some code finally. This is the source. First thing to keep in mind, we start from the types, right? We want a source of property changes that materializes to a not used. Sorry? Yeah, that's going to come next. Just bear with me. There's a reason for all this. So start with the types, right? Again, now this is a good moment to look around. This is actually why I grayed this out. To look around for any library that might already offer what you need before you start bashing some code to talk to Kafka, right? And I think this is a theme that I've already heard in other talks as well. It's always good to do some preliminary investigation and see what the community can provide for you. And this is actually one of the key strengths of Akka Streams as well. Community is going crazy around Akka Streams, providing all sorts of connectors. Alpaca project is a great example of it. I think one full talk is going to be dedicated to that later tomorrow, I believe. Now, especially for integration stages, is great to check out what the community can do for you. And in this example, we want to read from Kafka. So a very good idea would be to use reactive Kafka, right? And this is a stable library. It's been around for a while. It's actually currently maintained by the Akka team itself. So in this example, hopefully you can see how easy you can create a Kafka source just by calling consumer.planeSource. This kind of the simplest version of source that you can get. You just provide a bunch of settings, a topic. Now the settings itself, I've put 3 question marks there just to make the example as simple as possible. The deserialization logic essentially will need to be put in here. I just didn't want to clobber this slide too much, but essentially you get back from the library a source. What I wanted to focus on is that this source that you get back is not of the types you want, right? So these are the library types. It's a consumer record of a key and the value, which is what Kafka gives you back, and materializes to a control, right? Now, it's good practice not to leak these types outside of the stage. So this is why in the second part of the slide of the source, we actually use map and map materialize value combinator from Akka Streams to basically adjust the types that we get from the library to our own domain types. So now onto the processing flow. This is different. So this is not something we get off the shelf, right? So it's a completely different thing. We need to take care of the logic ourselves. So here's the types we need to fulfill. Again, keeping those in mind as a starting point. So the idea here is that custom stages like these ones, they need to be as thin as wrappers as possible around domain logic, right? So this is why in this example we define a service class using kind of DDD terminology here to perform the processing duties, and we call it property processing service, right? So assuming in this case that the validation logic is something CPU bound that we do in a synchronous way, we can use flow.from function from Akka streams to wrap a function around a flow, right? So this is super simple, but what we do here is we delegate the business logic to a service, and this guarantees a clean separation between whatever reactive stage you have and your business logic, right? So this helps readability and testability when your complexity grows. Essentially, if the complexity grows, you can add further abstractions layers by keeping this flow intact, right? The signature flow will stay like this, and you will kind of deep dive with your complexity within. So suppose we want to split this into two bits. So our processing is consisting of some validation and then some transformation, let's just say. This is something you can do in two places. You can either do it inside the service itself, or you can actually bubble up these two components to the stage level. And the question you need to ask yourself here, does your stage need to know about this complexity? If the answer is no, you can actually work within your service and maybe aggregate more service inside it and let the stage know nothing about this. Now, there are some possibility in which your stage needs to know about this. In fact, there is a catch when you're actually combining synchronous calls like these inside Akka streams. Essentially, when you link using map two of these calls, Akka will just slam them together in one single actor. So this means the pipelining will be effectively disabled through a section of your pipeline. And this is fine in most of the cases, which is why they did this by default. But if your computation is heavy enough, it can become a bottleneck. So they give you the possibility to force a manual asynchronous boundary between these two flows. And this is done by using this async call that you can see between these two little flows there. So this essentially tells Akka to run these two things independently as to within two different actors, right? So this has to happen at the stage level because it's essentially a reactive requirement. So you can see why whatever is reactive is handled in here, whatever is business logic related is handled down in our domain layer. Now, the AdWords storing logic, moving on, is equally simple. It follows the exact same principle. So we can wrap another service here that we can call AdWords service. And this guy will just go out and do whatever it needs calling Google, right? Now, the difference here, of course, is that this is something that does something IO based, right? So this is likely to have asynchronous behavior. So we can use map async here to parallelize and control the parallelization of our calls downstream to Google, right? And again, it's important to notice how this is separating the concerns between the reactive logic, that is the handling of the parallelism with the map async, and the actual business logic that is in the service. So other reactive behaviors here can be added to this stage whenever needed. So these APIs, like Google AdWords one, for instance, sometimes they have rate limitations, right? So they are not that clear, but they provide very conservative rate limiting. They just say 50 requests a second, right? So it's usually not true, but they give you that. So they're basically they can refuse stuff if it comes at a higher rate. So this is a typical use case for the throttle combinator, right? So, and it's actually a very good example of something that's kind of tricky to implement if you want to implement it yourself, right? Fortunately, you have something that like Akka streams to help you here. The throttle stage is just as it is one-liner. You can just give it a rate, like 50 elements per second. It allows you to specify a maximum burst, which is essentially if your source is silent for a while, and then it bursts a number of messages, it will just emit downstream only 50 at a time before starting to back pressure. And the mode is shaping, meaning it will not fail when the rate is higher upstream, but it will just back pressure. So, of course, if the producer rate exceeds 50 elements a second, the throttler will start back pressuring, right? So if the API that we call doesn't allow you to do any batching, that's just the only choice, right, that we have. However, sometimes API like these allow you to send a batch of changes, right? So this is something that can also be done very trivially using using Akka streams, using the batch combinator, right? So this is again another great example of something that it's not that trivial to implement on your own, unless you got something like Akka streams at your disposal. Now the batch combinator here, it works in a fold-like way, so you can easily see what it does. It just basically keep this list of states with all the messages, and whenever the batch reaches a max size of 5,000 in this case, it just forces the batch to go downstream. Now, the important aspect here is that this stage is back pressure aware, so it doesn't like simply batches elements or events in group of 5,000. It does batch only if the downstream is back pressure, right? So this can go a couple ways. Either Kafka is emitting events slower than AdWords can actually consume them, and in this case our batches will have size 1, right? So we will keep calling AdWords for each and every element that we have. If Kafka is faster than the consumer, then the batch stage will start batching them, right? Now, if when your batch reaches 5,000, it will get emitted anyway, right? This is because AdWords API, for instance, has a limitation of the size of the batch. So if you emit a batch which is like larger than 5,000, it might fail, right? So if when these batches are emitted, they can still exceed the throttling that is placed downstream, then the whole pipeline will start back pressuring because we don't have any other choice. Like we need to tell Kafka, please stop sending us stuff. So moving on to the error sync, I'm not going to spend a lot of time on this. This is probably you got the gist of this by now. Again, we use another service here that handles the errors, right? And in this case, we can use sync.forEach to call whatever this service provides. So the graph here is where everything comes together, right? So we have the type right there. We can just see how this becomes into code. Now, types first, we have a runnable graph that materializes to a future, right? So more code here. All we're going to need is all the stages that we've defined so far. It's a chunky type signature, the one you can see there. Although it tells you in one place all of the stages of your pipeline. So it might be kind of good to read through just to make sure you know all the events that might go on. Now, the flows we have here, they are not ready to be concatenated because there are these eithers in the way, right? So the types are not matching very well. We need an extra stage to divert the errors to our sync. And this is a stage, this divert error stage is a stage that can be implemented generically and concatenated to any flows that might produce errors, right? So we're going to see how that's done in a second, but if we assume that we have something like this at our disposal, we might have a way to actually concatenate these flows in a very linear way using via. Now note that at the end we use sync.ignore because we actually decide to throw away the positive signals that come back from AdWords. Although you might do something there, add more stages, do some logging, whatever. It's not. It's just to simplify this example. Now, going back to the diversion flow, let's deep dive into that for a bit because it's kind of the interesting bit topology-wise. This is essentially a flow that receives eithers and partition them, basically sending the errors to a sink of our choice and emitting the right-hand side of the eithers downstream, right? So it can be implemented in a generic way. So this being quite a common pattern has been made part of the Akka Streams API since last Feb. So this is from Akka 2.5.10. And essentially, there's something now that it's called divert2mat or divert2 in its simplest form. It takes a when parameter, which lets you specify when to divert, of course. And in our case is when our either is left. It lets you specify, of course, the sink where to divert stuff, right? And in this case, we add an extraction bit in front of the sink using contramap to extract the left-hand side before sending this to a sink. And this is actually safe in this case because only the left-hand side is going to be sent to this. So this kind of very compact way, there's a lot going on, but it's kind of very self-explanatory. Now note that before Akka 2.5.10, having an operator that does this would have to look like this, which is not as compact as you might notice. Now I'm not going to touch on the details of this, but if you just notice, it uses GraphDSL, right? The squiggly arrows there. So you might have seen this before. It's kind of a lower level DSL that Akka Streams provides. It does look tempting, definitely. So you might have been lured into Akka Streams looking at code like this. It's something that people tend to go overboard with. So just a word of advice there. It's not something that scales very well. It can be tempting to start implementing your whole pipeline using GraphDSL, and when the pipeline grows in size, you might be in trouble very quickly. So try and limit the scope of the GraphDSL as much as you can, using it only when you need it. And that's primarily when you need to do fan in and fan out. Now, moving on to the next bit, designing our stages, we have identified a bunch of domain elements, right? So this constitutes the domain, the business logic of our application. So whatever we have in this slide has been driven by the choices that we've made when designing the stage. So we need events representing changes, errors. We need services that provides the processing logic, that talk to Google AdWords, all this stuff. Then we're going to need a place where we manage the life cycle of our pipeline. So we still need things like failure handling. We need config management. We need to wire up our stages. We need to actually run the stream. So we have never seen actually the stream running anywhere here. So this layer is obviously kind of the entry point of our app. So essentially the stack looks a bit like this. We've ended up designing the green stuff, that is our stages, and then we let them drive the domain layer at the bottom, which contains the business logic. Now this doesn't know about Akka streams, of course. The application layer on top adds lifecycle management again, allows the application to be packaged, deployed, and scaled where you want. So the last topic I wanted to cover is testing of your pipeline. And of course, if you're a TDD freak or whatever, you might want to swap the two balls there. It's not my concern. I'm not making an assumption here. So our pipeline stack is quite a good match for a very old coding concept that's called the test pyramid, right? So you might have come across this. Now, two main concepts about this. One is tests are to be written at different granularities, right? And second, the more higher level you get, the fewer tests you should have. Well, this is fairly common practice, right? So if you stick to these concepts, you come up with a healthier, maintainable test suite, right? So you write lots of unit tests at the bottom, testing your domain. You write some more coarse-grained tests in the middle against your stages, and then you write very few high-level end-to-end tests that run the whole pipeline end-to-end. So let's quickly look at how this applies to the different layers of our application. So we start end-to-end. Now, our application here, our application test is going to look very much like this. It's a black box testing, basically. It's going to verify whatever side effects happen when you run your application. So all dependencies here are embedded. Note, in this case, we have KAFKA and Google AdWords web server to stub. So there might be pipelines with more than two. So these tests are quite complex and lengthy, both to code and to write, mainly because, to code and to run, mainly because you need to initialize these dependencies in a way. Maybe you start up a few Docker containers. You have to manage the shutdown of these. So writing exhaustive tests for your pipeline at this level is definitely not a good idea. So maybe a couple of scenarios here, nothing more than that. Now moving on to the graph, essentially testing the graph is testing the topology of our pipeline, right? So here you can test using fake stages. Now, test is a bit ugly here. In our example, we just have the diversion components in our pipeline topology-wise. So we're going to end up testing pretty much that if you test at the graph level. So there's no need to embed any dependencies here. It's essentially all the stages that you siphon into your graph are going to be faked using Akka Stream's DSL, right? So one advantage is that you don't need eventually blocks anymore, but still, this test is a side effect test, a side effect based test, so it's still quite complex to write. So at the stage level, there are several ways you can go about this, and it's definitely much simpler to write tests. So the main choice you have here is between the Akka Stream's test kit or just writing simple fake stages against the stage to be tested. So let's just quickly compare and contrast here. So let's take the KAFKA source, for example. So there's a few things we need to set up before we write the proper test. So we want an embedded KAFKA to run. We want some change that we publish to it. And then at this point, we can create our source, right? This is our source to be tested, right? So we create one. At this point, if we use test kit, the test will look like this. You can run your source against a test sink that materializes to a probe. And you can use this probe to request messages from the source and make expectations. So this is quite neat, although it's one extra DSL you need to kind of learn and make part of your team. So if you want to write simpler tests, you can also do it without introducing the test kit DSL. So you can just use fake stages like sync.head in this case. You just want one element to go through your stream, use sync.head. It just materializes to a future that contains the first element that passes through your stream. And then your stream is automatically killed by Akka Streams. Now, in case you need more messages in your test, you can use things like take with the number of messages you want in combination with sync.seek. And this is another kind of very quick way of testing your source. This will materialize to a future of a sequence of events. So you can then make assertions on top of this. So we've seen both test kit and fake stages approaches, if you want. They're both very valid. We tend to use this last approach a bit more because, again, you don't need one extra testing DSL. But they're both very valid. My feeling is that it's probably more powerful to use the test kit. But in case you're not working with custom stages or anything more complex than that, there's really not much of a point. So we've come to the end of this journey. Let's just quickly recap the key points. So stages, first of all, think about the stages that compose your pipeline. Start very simple and iteratively deep dive and use composability to deal with the complexity of your pipeline. Types, you have to spend time designing the types of your stage. They are the domain event that go through your pipeline. It's good to make error handling and side effects, other kind of side effects like audit, explicit in the types of your pipeline. And you can use materialized value to express control over your pipeline from the external world. When you implement a stage, you got two possibilities. Either you find something off the shelf, like reactive KAFKA, and you're all happy, but at this point you have to adapt the types into your own domain types, right? Or if you implement the stage yourself, it's good to separate the business logic modules from the reactive stages themselves for greater flexibility and testability. Tests, write tests on single stages using dummy Akka Stream components. It's much easier and simpler than writing tests on your whole pipeline. Now, it's good to go through these steps iteratively, maybe taking care of one stage at a time and build, of course, your pipeline progressively. One thing we believe in at HomeAway is evolutionary architecture. So this is about going to prod with the simplest possible approach, like slimming down the requirements as much as we can so we can get some good feedback. So this is akin to agile, of course. So we like to refine these 4 steps in multiple iterations. So in conclusion, I believe Akka Streams is a great piece of tech to build your pipelines. Now, I really hope that you might have got some ideas about how to think and design your pipelines and come out with a plan to roll them out to production using this toolkit. So I'd like to thank you very much for your time today. Let me just close this by saying that HomeAway is hiring engineers. We're based in Madrid and London, so in case you're interested in knowing more about the awesome stuff we do there, please get in touch. There you go. Thank you very much. Yeah, so that's a great question. So of course I've simplified this for the purpose of this example, but yeah, most of the times you might want to commit to Kafka after you've done whatever interesting is happening in your pipeline. So you've got a couple of ways to go about it. The best way would be to carry over the offset, of course, through your pipeline. You can use, again, expressive types to make it happen, separating data from metadata in a way. You might even go further and using more functional programming akin concepts, like using functors, for instance, to kind of map over the data that goes on in your pipeline just by setting the offset aside. You're probably familiar with this. Of course, it becomes a bit tricky if your pipeline is doing something more, a little bit more non-linear. Let's say if it's expanding one incoming element in more than one element, how do you deal with the offset? You're gonna need to put the offset at the very last. So it's a tricky problem. I agree. You need to take your use case in mind. There's not a silver bullet solution to solve this. You just need to be sure you carry your offset through your pipeline the best you can.